In last video, we worked on a linear regression model with one input, one weight and one line. Temperature predicting the cool drink sales. It worked, mathematically beautiful, but useless in real world. Nothing in real world depends on a single feature. For example, consider the sales. It depends on things like temperature of the day of the week, whether there is a cricket match, whether your competitor running a discount, and 47 more things which you haven't thought of. We'll handle all of this today. We'll cover multiple features, matrix math, and how gradient descent actually points to the lowest value of the loss curve. We'll visualize the loss function of our linear regression model, which we write the code for. We'll have a working linear regression model built from scratch, no shortcuts. Here is our model from the last video. Temperature on the x-axis, sales on the y-axis, one weight and one bias. It's beautiful and simple, but here is the issue. Real sales data doesn't care about your beautiful simple model, because some cold days might have massive sales like these ones, and some hot days might have terrible sales like these one. One feature like temperature doesn't explain everything. So we need more input and more context and more features. So consider this equation: y equal to w1x plus w2x2 plus w3x3 plus w4x4. Here the inputs are the temperature of the day of the week, whether there is a cricket match, whether your competitor runs any discount. Now our model needs 4 weights: w1, w2, w3 and w4. Each weight tells us how much does this feature affect the output. For example, consider w1 is a high value weight. If you increase the w1, it will increase the number of sales. Consider w3, which is closer to 0. If you increase the w3, then the sales will not be affected much. For example, if the w4 is negative, if you increase the w4, then we might decrease the sales. This is multiple linear regression, same intuition as before, but with just more weights, more inputs and more parameters to find out. But the question is, how are we going to handle this computationally? In our case, we just have 4 weights. We need to multiply the w1 with x1, w2 with x2. But consider that we are trying to predict a much more complex thing which has like 500 weights. Then how are we gonna multiply each of these? So this is where matrices come into picture. Before we touch matrices, let's make sure intuition is alright. So you have a dataset of 5 days of sales data with 4 features: temperature, day of the week, cricket match and the competitor discount. So here is the table. This table has a total of 5 rows, 5 data points for 5 days, 4 input columns which represent 4 features and 1 output column which represents the sales. Now just remember this. We'll get back to this table again. Now consider a simple linear regression with only one single feature. To get hands on the matrices, in this equation y equal to x dot w plus b, y is the output matrix, x is the input matrix and w is the weight, as we discussed in the previous video. X represents a set of inputs. Each row represents the temperature of the new day. This is the temperature of the first day, this is the temperature of the next day, and so on. These all represents the input feature, the single input feature which we considered in the previous video for our simple regression model. And y is a simple similar vector which is equivalent to x, but it stores the output of this equation after performing the dot product and adding the bias to it. With just one simple feature, w is simply a single element matrix with w1. In our multiple feature case, we have 4 weights. So a w will be a matrix with 4 elements in it. So remember, y is a one-dimensional matrix same as x, which is a single column output matrix. Similarly, x is the input matrix. We perform dot product between x and w, that is x dot w. This is crucial to get the output in a single dimensional vector with single column as y. So in machine learning, we call a single column matrix like x as a vector. Remember this so that you won't get confused in future when we use matrices with multiple dimensions. Let's trace one of the element x1. You substitute in place of x, multiply with w, you get some answer and add the bias to it, and you get the y value, and you store that y value in a new metric, output matrix. So this becomes your output matrix, and you repeat this process with x2, x3 and so on, multiply them with the weight and then add bias and store it to the y matrix. The original equation of our model is y equal to w1 x1 plus w2 x2 plus w3 x3 and plus w4 x4, where w1, w2 and w4 represents the features of the model. So we need to convert this complex equation into something much simpler, such as y equal to x dot w plus b. Remember the table from the previous one. Here we have 5 data points with 4 inputs and 1 output. Since x is the input matrix, we need to write the 4 input features as a matrix of x. The first row represents the inputs for day 1. Like on day 1, the temperature is 35 degrees Celsius. It's the 6th day of the week and there is a cricket match but no competitors discount. Similarly, second day we have 28 degrees Celsius, second day of the week, no cricket match but there is a competitors discount. So these all represents the input features for all 5 days. So in the bottom here, n into f represents the dimension of this matrix, which is equal to 5 by 4. This is a 5 by 4 matrix. Now W represents the matrix consisting of weights. We have 4 input features with 4 weights. So W equals to W1, W2, W3, W4. This matrix is of dimension 4 cross 1, which is represented here, where f is the number of features for any multimodal you want to build. So to get the predictions for day 1, you take the input from X matrix, that is the first row, and perform dot product on this row with the W matrix. So we get the equation like y1, where 1 represents the output of the first day. 35 times w1 plus 6 times w2 plus 1 times w3 and 0 times w4 plus the bias. Similarly, you repeat this for all the 5 inputs, y2, y3, y4 and so on. So here is the mathematical intuition of the dimensions. We are multiplying a matrix with n cross f dimensions and f cross 1 dimension. So when we multiply these two matrices, these two f's get eliminated and we are left with a matrix with n cross 1, which is a matrix with just single column consisting of the sales of that day. So this is our y cap, the output of the model for each input of the day. So we convert this complex equation into something simple as y equal to xw plus b, where x represents the input matrix consisting of inputs for all the 5 days, where the first one is temperature, day of the week, cricket match and the discount. And w represents the weights of this equation, w1, w2, w3 and w4. We perform dot product between these two matrices, add the bias to it and store the outputs in the y cap, where this y cap is a matrix with n cross 1 dimensions. So you just simply substitute each row into the equation and get the output, store the y value into the y cap matrix. This is your multi-feature model with multiple input features like the temperature, sales and discount. While multiplying the matrices, remember that the inner dimensions must match, like f and f here, and the result will be the outer dimensions like n cross 1 here. Anytime you perform a matrix multiplication, the inner dimensions of the two matrices must match. Only then we get the output with the outer dimensions like n cross n here. The loss function, gradient and update rules are all the same, but just with matrix derivatives instead of the scalar derivatives like we did in the simple linear regression. The loss function we'll be using is mean squared error, which is equal to 1 by n times the sum of the squared errors, same as before. In gradient, derivative of the loss function with respect to w is 2 by n times of x transpose. Remember this word transpose, I'll explain it to you. X transpose the times of error, and the derivative of loss function with respect to bias is same as before, 2 by n times of the sum of errors. So why are we performing the transpose operation here instead of directly multiplying the x with the error as we derived from the loss function? So remember earlier I mentioned the input dimensions of any two matrices you are trying to multiply must match each other, so that you will get the output like n cross 1 without any errors, which is mathematically correct. So here our y cap minus y matrix is a dimension of n cross 1 and x is in the dimensions of n cross f. So when we multiply these two, we get the equation n cross d dot n cross 1. As we can see, the inner dimensions are not same. We cannot perform this matrix multiplication. So this is mathematically not possible. So what do we do instead is we take the transpose. Transpose simply means, for example, consider this matrix X with elements 1, 2, 3 and 4. So after we perform transpose operation, the matrix becomes 1, 3, 2 and 4. We simply interchange the columns into rows. This is what the transpose actually performs. So we transpose the X, which becomes X transpose times of y cap minus 5. Now the dimensions are d cross n times of n cross n. We can see here the inner dimensions of these two matrices match. So we can multiply these matrices and our output will have the dimensions of d cross n, which is mathematically correct. So that's why we use the term x transpose instead of x while calculating the derivative of loss function with respect to the weight. And same as earlier, we update the values of w and the bias by subtracting the multiplied value of their derivatives with the learning rate, which is explained in my previous video. So now we are going to write code for this multiple linear regression model. We need to get familiar with these three libraries, NumPy, Pandas and Matplotlib. I'll be giving you guys a brief overview of these three libraries with just the minimum things required to build this linear regression model. If you are familiar with these three libraries, then feel free to skim through this portion of the video. You can access this notebook from the repository URL mentioned in the description. So here is the brief overview of the NumPy library. We import this library using this line, import NumPy as MP. In NumPy, we use the method dot arrays in order to declare an array. The variable a stores an array with one row and 4 columns with the elements 1, 2, 3 and 4. And b is a two-dimensional array which stores the elements 1, 2 and 3, 4, where this is the first row and this is the second row. So it has 2 rows and 2 columns. So let's print array A. Here we can see it is a one-dimensional array with 1 row and 4 columns and with the elements 1, 2, 3 and 4. Let's print the array B. It is a two-dimensional array with elements 1, 2, 3 and 4. We can use the method dot shape method in order to print the dimensions of these arrays. So let's print out the dimensions. A is an array of dimension 4, 1 and B is an array of dimension 2, 2. So B is a matrix of two-dimensional array which consists of elements 1, 2, 3 and 4. We can perform operations on these two matrices like the multiplication and the dot product. So let's multiply the matrix A with 2. Let's print the output. So if we multiply the matrix A with 2, this multiplies the number element wise. So the elements 1, 2, 3, 4 are multiplied by 2 and we get the output with an array storing 2, 4, 6, 8. This is the multiplication over an array. We can perform the dot product between two matrices. So here the at sign represents the dot product of these two vectors, a dot a. So which is equivalent to 1 into 1 plus 2 into 2 plus 3 into 3 plus 4 into 4. This is the dot product value of a dot a. So let's print the output. We get 30. So value of this a dot a is 30. Let's consider much familiar examples, x and w. So earlier we wrote the equation for our linear regression model as y equal to x dot w plus b, where we perform the dot product between x and w. So let's consider those variables, x with a 3 cross 2 matrix and w is a 2 cross 1 matrix. So let's perform dot product between these two vectors. We should get a matrix with 3 rows and 1 column, which is called as a vector y as an output. So let's print this. See, we got an output with 1 column and 3 rows with the elements 5, 11 and 7. So earlier in our regression model we had bias to the equation y equal to x dot w plus b. So let's add some bias to this equation. Let's say we add 3 and print the output. See, now the 5 plus 3 8, 11 plus 3 14 and 17 plus 3 20. So this is exactly how we get the y output as a matrix of single column, which is also called as a vector. In our models at start we choose random values of weights and then we improve over the time using the gradient and gradient descent. So this is a syntax to generate random numbers using NumPy. We use the random library provided by the NumPy, and random represents the Gaussian distribution of the random numbers generated. So the numbers generated will be lies between -1 to +1 and they rarely cross 3 to -3 in rare cases. And the 4, 1 represents the shape of the output as the shape of the matrix, output matrix. It's 4 cross 1 here. So let's print w random here. So this is a 4 cross 1 dimension vector with random numbers generated. So if we run this same code again, we get different numbers. See, this is what we use the dot random method and generate random weights, put these into the y equal to x dot w plus b equation and train our model and improve the weights over the time by using gradient descent. And also one more thing we'll be requiring is the transpose operation. So transpose is performed using this symbol dot caps t, which will flip the rows and columns as I mentioned previously. So let's perform the transpose operation on the matrix x. So better let's just print x here and print the x dot t again. So let's first print x here. Let's run this code. See, this is how the x at first with 2 columns and 3 rows, 1 2 3 4 and 5 6. Now after performing transpose operation on the x, we got the output as 3 columns and 2 rows. So this is how we use the transpose operation. This is the brief introduction about NumPy. Let's continue with the pandas library. So this line helps us to import the pandas library. Import pandas as PD. We load the data using the .read CSV method if it's a CSV file, and you can paste the local path for that file if the dataset is on your system, or you can also paste the raw GitHub URL, which I did in this case. So the syntax to load that data is df equals to pd.read CSV file if that's a CSV file. df stands for a data frame. Data frame is a core data structure in pandas which is used to manipulate the CSV files. Now let's get to the first method. If you want to have a brief overview of the table, like what are the different types of columns in it and what are the ranges of the values in the spreadsheet, we can use the method .head, which prints out the first 5 rows of the spreadsheet. So let's run this. As we can see here, the output consists of a temperature, day of the week, cricket match, completer discount and sales. 5 columns and 5 rows. These are the first 5 rows in the spreadsheet. The .head method helps us to print the first 5 rows of the spreadsheet. And we use the .shape attribute to print a tuple consisting of number of rows and columns in a table, similar to the arrays method which we did in the NumPy. So let's print out the dot shape attribute, it prints a tuple 200 comma 5, where 200 represents the number of rows in the spreadsheet and 5 represent the columns, as we confirmed it from the previous output where the dot head method output the 5 columns. So the dot shape attribute helps us to print the shape of the dataset. Now the dot info method helps us to get the exact data types of the columns and whether does it have a null values or not. So if we run this is the output. Temperature and its data type, day of the week and its data type, total number of non-null values and null values, total memory use, different types of data types. It gives us a brief overview of what the data type of each column is. And the dot describe methods gives us a general statistical view of each column, like the minimum value, maximum value, mean, standard deviation, etc. Let's print this out. So for all the 5 columns, we got the count, mean of the particular column, standard deviation, minimum value, maximum value, etc. It gives us a general statistical view of each column. Now, as we saw earlier, when we use the method dot head, our table consists of these 5 columns. If you remember from earlier topic, our equation is y equal to x dot w plus b, where x is a matrix of 4 columns with exactly these 4 inputs: temperature, day of the week, cricket match, and competitor discount. And the sales is the output which we are trying to predict, y in our case. So we need to split this table into the input part with these 4 columns and the output. So that's what we are doing in here. So the syntax for that is x equal to df of double squared braces. So this double square braces helps us to return the values of multiple features. When we run this line of code till exact this point, the pandas returns a 2-dimensional data frame, and we use the dot values attribute over it to convert it into a 2-dimensional NumPy array, which is much easier for calculations. Similarly, df of sales, which gives us a 1-dimensional data frame array in pandas, and we use the dot values method over it similarly to convert it into a 1-dimensional array in NumPys, which is easy to manipulate with. Now let's get to the third library, which is Matplotlib. We import this library as matplotlib.pyplot as PLT. So we'll be using PLT in this entire section. So using this library, we can plot different types of simple graphs to the canvas. So we can plot 3 types of graphs, which are line plot, scatter plot, and multiple plots. We'll get into these things. So let's first talk about the line plot. We use the method dot plot to plot a line plot. So the 2 lists you can see inside this dot plot method are the coordinates. The first list stands for the x coordinates and the second list represents the y coordinates. These two together form the coordinates like 1, 1, 2, 4, 3, 9, and 4, 16. These will later become the coordinates, which will be plotted onto the graph, and the Matplotlib library draws a straight line between each of these points, forming a line plot. So we use the method .xLabel to label the x-axis. So we can replace anything in place of this x. Similarly, we use the method .ylabel to label the y-axis, and .title to give a title to our plot. We can replace anything in place of this simple plot. And finally, we should use the method .show in order to print our graph to the canvas. Let's run this plot. So here we can see we got a simple plot. Our first point is 1, 1, 2, 4, 3, 9, and 4, 16. And these 4 points are joined using a straight line, which becomes a simple plot or a line plot. Now let's get to the scatter plot. Scatter plot, in which you just plot the points on the graph and you don't join the individual points, just leaving the points on the graph. Similarly, but we use dot scatter method to plot a scatter plot. Same as earlier, the first list represents the x coordinates and the second list represents the y coordinates. And this color blue represents the colors of the coordinates. Finally, we use the dot show method to print the output to the canvas. Let's run this. So this is a scatter plot, which only consists of the coordinate points. Now let's get to the multiple plots, where we can plot multiple graphs side by side. So figure comma axis equal to plot dot subplots 1, 2. Here 1, 2 represents the number of rows and columns. So 1, 2 represents one single row and 2 plots consisting of 2 columns consisting of 2 plots, and fixed size equal to 12, 5 represents the size of this row and column in inches, 12 inches and 5 inches. The axis here is an array referencing the two plots. So axis of 0 represents the first plot and axis of 1 represents the second plot, which we are going to print. So the first plot has the coordinates of these x and y coordinates. Title set to left title. We here use a different method, which is dot set title method instead of a dot title method which we used earlier. So let's print the output to the canvas. This is the axis of 0, which is the first graph on the left side, and this is axis of 1, which is the right plot. This is how we use Matplotlib to plot the graphs. Now let's move on to the next topic, which is data pre-processing. Now here where we start actually building the linear regression model. The first step is data pre-processing, which consists of two more steps. And the first one is data splitting or separating the inputs from outputs. As we discussed in the pandas library, when we used the method dot head, which gave us the output of first 5 rows, those rows consist of 5 columns as well, which contains 4 features: temperature, day of the week, cricket match, and the competitor discount, along with the sales. Here the 4 features are our inputs and sales is the output which we are trying to predict from the 4 features. So we need to separate these first 4 columns with the last output column. So that's what we are doing here. The syntax is known, which we discussed in the pandas section. Data frames of 2 square parentheses, which represents a 2-dimensional data frame consisting of temperature, day of the week, cricket match, and competitor discount. And we use the method dot values to convert the 2-dimensional data frame into a usable 2-dimensional NumPy array. Similarly, we use the data frame of sales, which gives a 1-dimensional data frame of sales, and we use the dot values method to convert it into a usable array or a vector in NumPy. And we use the dot value method to convert it into a usable array or a vector in NumPy. Let me tell you why we use the dot reshape method in here. When we convert this 1-dimensional data frame into a 1-dimensional NumPy array using the dot values method, it won't convert this 1-dimensional data frame into a vertical single column vector. Instead, it converts it into a single row 1-dimensional array. So we use the dot reshape method to get back into the single column vector shape. So that's why we use the dot reshape method in here. So let's print the output. Let's print the shape of each x and y, which is our input and output splits. As we can see, the shape of the x is 200, 4, which represents the 200 data frames consisting of 4 features, and the y shape is 200 data points consisting of one single sales out. So let's move on to the next process in the data pre-processing. That's the second step, where we split the dataset into train and test split, which we covered in the video 2. We split the dataset into 80% of the train split and 20% of the test split. So as we set here n equal to 200, which consists of 200 data points, we need to split 80% of this 200 into training dataset and 20% of this dataset into testing dataset. The number we are going to get here is 160. 0.8 times of 200 is 160. So 160 data points used for training and 40 for testing. So we are going to currently we just have one single x input variable and y as the output variable, but we need to split the x into the training and testing split as well as y into training and testing. So that's what we are doing in this step. The x underscore train list is set to the original x squared braces of semicolon of split. This syntax is called as list slicing. So what this actually represents is that we start from 0, that is out of the 200 rows in the dataset, we start from 0 and stop right at the split, which is exclusive. So we start at 0 and we stop at split. The value of split we got is 160. This x underscore train consists of starts from 0 and ends at 159. Similarly, the x underscore test is referred to x of split semicolon. This syntax represents we start at split, that is at 160, this is inclusive, and go through the dataset till the end. So we start at 160 and end at 200, which is inclusive. So the x underscore train consists of data points from 0 to 159 and x underscore test consists of data points from 160 to 200. 80% split, 20% split. Similarly, we repeat this with the output y underscore train and y underscore test. Let's print the shape of x train and x shape. So this is a training dataset, shape of the training dataset x, which is 160, 4, 160 rows and 4 input features. Similarly, the testing dataset consisting of 40 rows and 4 input features. Now here is the most important part of the model, that is feature scaling. Here is the problem. We have 4 input features The first one, temperature lies between the range of 15 to 45 degrees centigrade. Day of the week lies between the range of 1 to 7, and the sales value lies between the range of 200 to 1000. These features are on completely different scales. When the gradient descent runs, it treats all features equally in terms of step size. A large scale feature dominates the gradient and the model takes forever to converge or never converges. Let me show you what I mean when the model never converges. So assume this is our loss function. Here is the equation of it, which is z equal to 0.2 times of x square plus 0.2 times of y square. Here, as you can see, the coefficients of x square and y square are scaled, means they are in closer range. So we can see this is the curve of this function. So what do you mean by gradient descent traversal or convergence? Imagine dropping a spherical ball or a sphere into this surface and trace its path. As soon as you leave the ball from any of these edges, it will settle down at the bottom of the curve. That's what the gradient descent is trying to do, finding the global or local minimum of the curve. In this case, if we leave the ball here, it rolls down to the bottom of this shape and settles it down here. This is what happens with the scale feature. Now let's consider an unscaled feature and see how does the sphere behaves when we drop into it. So this is our new curve with the coefficients of x square being 0.2 and y square being 100. Look how thin the curve is. Now imagine dropping a ball over here. It goes to the bottom, then bounces back at this side, then again goes to the bottom, and it continues oscillating and takes forever to settle down at the bottom in the worst cases. So this is the visualization of a unscaled feature. Let me show you a real example of a complex loss function. This is a loss function for a very complex model. Let me show you what the gradient actually points out to. Consider this part of the curve. The gradient actually tells us the pointing direction of the slope. So this is the arrow which points to the direction of the gradient or the slope of the curve. You can see this curve exactly looks as I visualized in my previous video, where I mentioned that the loss function in three-dimensional space looks like a landscape containing several mountains and valleys. See, these spikes here are called as local minima. Imagine dropping a spherical ball again from this edge. The ball might settle down at any of these local minima, and that's good enough for us because we are trying to find out the local minima for the loss function. We don't need to target this global minimum of the loss function. So let me show you the gradient descent, like the visualization of dropping a spherical sphere or a ball. So if I click right here, you will see an arrow dropping down to the bottom, trying to find a local minima. So this is the gradient descent doing its work, trying to settle at a local minima. This is exactly how the gradient descent works to find the local minima or global minima of the loss curve. Now let's get back to our problem. So the solution for this is normalize everything to the same scale. We use standard deviation, subtract the mean from the feature and divide it by the standard deviation of that value. So the formula for this is x minus mu by sigma, where mu is the mean of the feature and sigma is the standard deviation. This is how we normalize every feature. And remember the critical rule, you calculate mean and standard deviation on training data only. Then apply the same values to the test data. Never fit the scalar on test data. That would be leaking the information about the test set into your pre-processing. We call that data leakage. Your model cheats without knowing it and you get a fake good results. See, look here, we are only calculating the mean and standard deviation for training set and using the same values for normalizing the test set. In this model, we are normalizing both y and x tests, both input and output features. Let's move on to building the main linear regression model. So this is the structure of the model. Object linear regression. These are the default values of learning rate and the number of epochs. I have mentioned in my previous video what the learning rate and epochs are. This is the method or function we use to train our model. It has total of 4 main steps, same as I mentioned in my first video and second video. This is where we initialize the random values for all the weights in the model and we start with the bias as 0. So for each epoch in the range stands for the number of epochs, the default value, or else the number of epochs you have passed to the method. So for each epoch, there will be a forward pass calculating the loss and backward pass. Backward pass stands for the gradient descent and then updating the weights and the biases. Forward pass is exactly same as the equation we have seen before. y predicted equal to x dot, this is at sign represents the dot product, x dot weight plus bias. This is the equation we have seen earlier already, y equal to x dot w plus b. And calculating the loss function, first we calculate the error, then the mean of the squared error. So this is equivalent to yi minus y. This is the error of the function. And if we square this and divide it by the total number of inputs, if we square this and divide it by the total number of data points, then it becomes the mean squared error. Next comes the backward pass, which is the gradient descent. This is exactly what I've mentioned previously. The value of derivative of loss function with respect to w equals to 2 by n times of x transpose times of the error. Similarly, we calculate the derivative of loss function with respect to b, and then we update both the weight and the bias using the same formula, w equal to w minus learning rate into the derivative of loss function with respect to that specific variable. Then this is to print each epoch to show the progress of the model, and these are just used to plot the graphs after training the model for evaluation purposes. Now here comes the training and results. We create a model, linear regression, passing the learning rate and epoch. Here we chose the learning rate of 0.1 and 1000 epochs. This single line trains the entire model. So we need to call the dot fit method and pass the scaled versions of the x underscore train and y underscore train, which are the 80% of the training dataset from the 200 entries. So x consists of 160 rows and 4 features, and y consists of 160 rows with a single column. So these will be passed on to the model. Now let's first scale the features, then run the model. Now create the model and train it. Here we gave 1000 epochs, so the model has trained. All the 1000 epochs are complete. The loss function has decreased from 1 to 0.09 in the first 100 epochs itself. So let's check the learned parameters. So these are the learned parameters of the model, which are exactly what you're thinking of. These are the coefficients of x1, x2, x3 and x4, and finally the bias is 0. Here we got the bias as 0 because we used the scaled feature for both input and output. And also remember the fact that these learned weights or the learned parameters are not the exact parameters of the line equation, because these are the parameters that we got for the scaled input features, not the original input features of temperature line between 15 to 45 or the day of the week between 1 to 7. These are the weights which we got for the scaled features. So these are completely different from the original weights of an unscaled feature. But we cannot train our model on unscaled features because the gradient descent never converges to any local minima or global minima, or takes forever to converge to a local minima or the global minima. So we use scaled or normalized features to build the model, and these are our learned weights. So let's test our model. This is the code you can go through for plotting the graphs between the number of epochs or loss curves, and the exact scattered plot and the line through them. So let me run this. Here is our beautiful model. This is exactly what we are looking for. A clean straight line passing through all the data points we have given to the model. This is your first linear regression model that you have built from scratch, learning every concept, learning all the 4 steps in training a model, forward pass, feeding the data to the model predicts the output, you calculate the loss function, then perform gradient descent on the loss function, find out the new local minima values and update the weights and biases to correct the model every time. And finally, we get this clean straight line passing through the data points. So now we can predict the future values for any given temperature of the day, any day of the week, whether there is a cricket match or not, whether your competitor runs any discount on the cool drinks. You can predict the sales of that day using this model. So this is your very first linear regression model. The plot one is the loss curve. This should drop fast at first and then flatten out. If it doesn't drop, then the learning rate is wrong. If it drops and then shoots back up, then the learning rate is too high. If it barely moves, learning rate is too slow. Plot 2 shows us the predicted and actual values. Predicted versus actual. The point should be very close to the red diagonal line. The closer to the line, the better the model is. Points scatter randomly around it. Noise we can't explain. That's fine. Points consistently above or below the line. That's systematic error, and that's a problem. But our model is perfectly lined up with all the points and passes through them, predicting the correct values. plot 3 is the residuals, errors plotted against the predictions. If you see any other patterns like a curve or any clusters or trends in that residual curve, your linear model is missing something and the relationship between the features is not linear. So we need to use any other different kinds of model. More on that when we hit the neural networks. And the next video is about logistic regression. We deal with sigmoid functions, same math, same almost similar code. We'll again build that model from scratch, and you can find the notebook and code for this entire video in the description. You will find the GitHub repo and you can get the code from there. Thank you.